All right, hello everybody. Welcome to WebAssembly Unleashed, your source for news and views about the world of WebAssembly. After 2 solid years of episodes, can you believe it? We've explored the heights and the depths of the Wasm world, and now I guess we're ready to go diagonal. I'm your host, Joel Moses, and joining me is my regular co-host, Oscar Spencer. How you doing, Oscar?
You know, I'm doing pretty well today. It's a nice, beautiful, sunny day.
Oh, yes. Now, as Wasm aficionados, we're dedicated to the success of this technology, and the fact you're listening in means you are as well, and we thank you for joining us. And if you've hit that like and subscribe button in the past, doubly so. If it's your first time with us, welcome. We try to accept all comers. We're happy to have you, and make sure to subscribe. Today, we're going to introduce you to 2 people doing some interesting work in the WebAssembly community that we've gotten to know over the past few months. They're doing interesting work to make Wasm more secure and Wasm easier to debug. But first, our normal pleasantries. We always start with a quick rundown of what we've seen inside the community that's compelling or important. And Oscar, I think there's something from Microsoft this time, right?
You know, there is. It's Wasm, if you haven't seen it. So this is a really interesting project to come out of Microsoft, and I guess maybe Microsoft GitHub. I don't know where they're trying to spin it, their angle here. But so, AI agents right now are all the rage. Like, that's the big thing, right? And so these agents, right, like their goal is, hey, I want to complete some task for you, and maybe I don't know how to do it exactly myself, but maybe if I had the right tools, I'd be able to do it, right? And so as we start looking at AI, trying to behave in this type of way, we need secure systems that these AIs are allowed to access, right? So the Wasm project basically bridges the WebAssembly component model with the model context protocol. So the MCP, for folks who aren't familiar, it's sort of just a standardized protocol for AI agents to be able to interact with, different tooling and actually get tasks done. So the big idea here is, since we have WebAssembly components, they actually provide a secure sandbox way to actually accomplish tasks. So this is actually a really big deal, because one of the biggest concerns that I personally have in this, AI age, right, is having AI go and just have access to do things that it probably shouldn't be able to do on its own. And so something like WebAssembly's capability-based security gives me peace of mind knowing, hey, this thing isn't going to say, go delete my production database.
Right.
Go off the road.
Not that happens, right?
Yeah, not that happens, right? But, so this is actually a really big deal, because in particular, Wasm allows an agent to go, to like an OCI registry, look for Wasm components that are able to accomplish this particular task, download it, get consent from the user, like, hey, okay, I'm going to take these actions, and then sort of move forward. That's actually a big freaking deal. This is actually super cool. And this is a fantastic use of Wasm components. So I'm really excited for this project. I think it's going to be great for Wasm components in general. It's going to be a huge uptick in just seeing people publishing components. But this is exciting. What do you think about this sort of thing?
It's really cool. Secure and bounded tools for AI agents. It seems like a kind of what component model was designed to enable, and to see Microsoft putting its time and attention into this and using WebAssembly as the carrier. I think it signals something really interesting for the future.
Oh yes, so
it's fantastic.
A bright WebAssembly future ahead, as always.
Oh, definitely. Speaking of that, it's time to introduce our special guests. That's right, we've got a twofer today. Joining us are Khan Karimov and Arjun Ramesh, 2 doctoral track students at programs at University of Utah and Carnegie Mellon, respectively, who we have gotten personally to know as they worked alongside us as interns. So we thought it'd be fun to do 2 things. First of all, get a perspective from them about the world of academia and the view of WebAssembly from inside academia, and then hear a little bit about their chosen areas of research. So, Khan, Arjun, welcome.
Thank you.
Thank you.
Khan, let's start with you. Why don't you tell our audience a little bit about yourself?
Hey, my name is Khan. It's pronounced like Wrath of Khan from Star Trek, but I've never seen it. So I am a 4th-year PhD student in computer science at the University of Utah, and my research has been around fuzzing WebAssembly implementations. So I've been doing research generally about the software testing and programming languages. So just find out more bugs. I make it my business to find more bugs in Wasm implementation that claim to be so safe and secure.
Keeping all of us honest, I guess, is what you're saying. That's great. So, let's talk a little bit about why WebAssembly. And a PhD candidate student has a lot of chosen areas of study that they can focus on. But why did you choose WebAssembly?
So when I started reading about the WebAssembly, I realized it says that it's safe, it is portable, it is simple, at least from user's point, and it is so safe and secure. So I think, are we getting some silver points in software engineering? Because I always believed what Fred Brooks said in 1986, like, we don't have silver bullets in software engineering. You cannot have something that's safe, that's performance efficient, that is simple. And I said, hey, that's interesting. But as a security person, I can tell that it's not so safe. Let me just try to find it out. Like a detective would always love to find a case that's full of mysteries. As a software testing person, I would love to find bugs in a system that claims to be safe and secure. So that was the first and primary reason.
So you're a born skeptic, is what I'm hearing.
Yes.
Okay.
And it took me for a while to convince my advisor.
Okay. Arjun, let's move over to you, and I'm going to ask you the same question, but why don't you start by introducing yourself?
Yeah. Hey, I'm Arjun. I'm a fifth-year PhD student at this point. Oh God, I'm old. Fifth-year PhD student at Carnegie Mellon. And I work a lot on WebAssembly in edge computing and more maybe embedded and resource-efficient use cases. Yeah, I think it's kind of interesting because I started off in undergrad sort of doing computer architecture and working really in the nitty-gritties of hardware, writing Verilog, building like all the low-level stuff that your software runs on. When I moved to my PhD, I sort of moved to this embedded system space and tried to see like, okay, is there a way I can move up the stack and sort of work in more interesting spaces in embedded systems and edge computing? And this was sort of the time when Wasm started getting some traction outside of the browser. People had started talking about it, but it was primarily people in like the security and programming languages spaces. You talk to anyone else in a system space where I'm from, and they're like, what's WebAssembly? Is it just like some random browser tool that no one knows of? Is it like a JavaScript variant, et cetera, et cetera? So that's sort of what got me started looking into WebAssembly. And, there are all these nice things we like about WebAssembly. Khan's mentioned them: security, portability. Like this should be something we want in all systems, not just browsers. So that's what kind of got me excited on exploring this in this niche use case for embedded and edge computing use cases.
Now, you worked on while you were attached to us a concept called time travel debugging, and we're going to dig into that a little bit more. But why the focus on debugging in as it relates to like embedded systems? What's important about that?
Yeah. So that's interesting because even today in 2025, people debug embedded systems by connecting physical cables to your system and reading UART ports and looking at ones and zeros on the screen, right? Embedded systems are, in all practical purposes, sort of a little fickle, hard to debug, and you don't really have a lot of resources on here. Like today, we have these really complicated debuggers that you can build on like your server-side machines, and you can run them. You have the resources to do that. When you're running something in real time on something that's resource constrained, it's not really easy for you to enable debugging techniques. And that's honestly why people do this today. They use things like oscilloscopes. They use things like, UART debug hardware. And at the same time, we're sort of moving towards this direction where we're not just running embedded systems. We're running things on the cloud. We're running things on the edge. So we have all of these distributed compute. So how can we unify our debuggability across all of these? And that's what I think makes Wasm really interesting, because it provides this portable platform. It provides us this base on which we can build debug infrastructure across all realms of computing. And that's what I sort of find interesting.
Yeah, I love that sort of the both of you decided to work on things that are sort of all about just making WebAssembly better in general. And so as a WebAssembly fan, that makes me really excited. But so Khan, going back over to you. So you decided to focus around particularly the area of fuzzing. Why fuzzing and not any other method of finding bugs?
Okay, I can just talk about the whole abstraction and its introduction of my paper here. Why Wasm?
Sure, dig into it.
Yeah. So fuzzing is cheap, and you can just have a simple tool, and there are already existing tools. The first thing, it's cheap. You can just give okay, let's start like, what's fuzzing? Fuzzing entails providing random inputs to the system under test in order to find bugs and crashes. But how we are supposed to find those bugs, especially in a system under test like WebAssembly, that's mostly deterministic and has a great specification. So like it's like a mathematics, and we have two calculators like Wasm time and Whammer, and we are supposed to find out if they implement the same specification correctly. So we have to give like 2 + 2 to both of them and to find out if the result is 4. So just this idea of giving inputs to the system under test is actually called fuzzing. And that's why this inexpensive and the very easy and the fast method of fuzzing just makes it better to find bugs in Wasm and other kind of programming language implementations. I mean, there are some other existing, some people ask me, hey, what's the difference between unit testing and the fuzzing? And I'm like, that's where you draw the line, like, because that's what you call fuzzing.
Yeah, that makes sense to me. And so in particular, why don't you tell us a little bit about exactly what you worked on during your internship at F5?
Sure. So WebAssembly is getting the new proposals, like it's thread proposals, GC proposals, and one of the newest one, I would say, it's a garbage collection proposal that personally makes me excited because it's something great. Now we have the
it makes
GC.
all of us very excited.
Yes, yeah. So, but I have just a phrase like, don't try it until you fuzz it. If you are implementing the GC proposal on Wasm time, first of all, you have to fuzz it and you have to make sure that it's secure. So I personally worked on the fuzzing garbage collection proposal that's implemented on Wasm time. It's something very interesting because I have hardly seen any papers how to fuzz GC and what's the GC bugs.
Got it.
And so for what you've implemented so far, how has the like, I imagine you've got fuzzers running at this point. How has it been going? Have you uncovered anything yet?
Yes, we've got some false positives. I think
happens.
That happens all the time. And I think we are gonna get, because we're still working on fuzzing garbage collection proposals. And the good news is that my advisor and decided to work on as my next project. And actually at this point, Nick, my advisor, and I, we can say that we are about to collaborate with F5 on fuzzing GC. So, yes.
Fantastic.
And, thank you. And the point is like fuzzing garbage collection proposals in WebAssembly is different from fuzzing GC in general. Because like, if fuzzing GC, you would say, hey, what's a GC bug? Okay, what's a garbage collector? It boils down to a graph theory. We have edges and they are connected to each other, and your GC implementation is supposed to find out if it's the object is live, do not collect it. If it's not live, just collect that garbage. So a bug would be if the object is still live, just do not, if it's collected, it's a bug. If it's not live but not collected, it's a bug. However, we are having types in WebAssembly. So, and there's some programming language, object-oriented programming language that have deep inheritance, and when we translate to the WebAssembly, we are supposed to translate it correctly. And that's why we have to generate WebAssembly models that specifically target this language features in order to find to these bugs. That's actually what makes it a question open to research. How you correctly translate the GC from another object-oriented programming language or another programming language that's using a garbage collector to WebAssembly, because then WebAssembly takes care of this memory management here.
Got it. Well, thank you for giving us a slogan for T-shirts. Don't try it till you fuzz it.
Yeah, I love
that. That's a good one. Arjun, I want to move over to you and talk about your project. So you focused on debuggability, which I think is a really interesting thing to focus on, and I think that component model gives new capabilities and new possibilities for the area of debugging. Why don't you tell us about some of your research?
Yeah. So at my internship at F5, sort of the grand vision that I was working towards is this idea of time travel debugging, which I'll get to. But kind of good news on my side as well is that I'm going to continue working on this for the coming
Awesome.
months, collaborating with F5 and Chris at F5, and hopefully get some cool research out of this.
Nice.
Yeah, so I think sort of the grand vision is this idea of if we have a deterministic model of execution, we should have the means of collecting traces of programs that are run possibly in production. And when we have things like crashes, we want to be able to easily trace back and debug the root cause of bugs that cause this crash. So what we'd want is essentially a way to have some notion of a recording of an execution that we can then skim through, not just forwards, but also backwards. And in fact, the backwards case is what's most useful. So if you have a trace that's 2 hours long, for instance, and you hit a crash, most often when you debug something, you want to kind of go up the chain, not back down. And if it's a long trace, you end up having to, if you're running it just in the forward direction, you need to start all the way from the back just to go to 1 hour, 58 minutes or whatever, right? So sort of the goal I've been working towards time travel debugging involves a lot of simple components that need to kind of come together. And WebAssembly kind of offers a really nice platform for this. Like I talked about earlier, we have this portable platform, which means it can operate on any hardware and across all languages. And this makes it interesting because the current state of the art is this technology called RR, which is essentially built to and tailor-made for x86 chips on specific Linux kernel versions. What we see is potentially a use case for something across all languages and all hardware, which is really exciting. But WebAssembly and the component model together offer this really nice deterministic semantics at both not just the compute layer, which is WebAssembly, but also the interface layer to the component model. So the nice thing is by having both of these, we can actually model sort of the boundaries of non-determinism really well at both the compute and the interface level. And so if anything is implemented in terms of the semantics of component model and WIT, which is the WebAssembly interface type system, we can then model sort of the non-determinism in a common fashion and make this sort of deterministic debuggability possible. So the first step that I did in this regard was just have a simple way of taking a component in WebAssembly, running it, generating sort of a trace that you can then replay deterministically such that it operates the same way when you replay it and runs through the entire WebAssembly component as it ran in production or when you recorded it. And so sort of from there, we can start thinking about more interesting things, which is now that I have a replay, can I run a replay with profiling? So now maybe you can profile the execution that crashed. Or can I run the replay with debug info enabled? Can I run the replay with some sort of caching enabled? And so there are all these kinds of like tools you can play with once you have a replay, because it's essentially a reproducible execution.
Yeah, so I know some folks' concern with like record replay, type of debugging is its impact on performance. And one of the things that we love about WebAssembly is that WebAssembly is very fast. But if I'm going to record this thing, it sounds like that would make it really slow. What were the impacts on performance that you saw when you did this?
Yeah, so this is actually interesting because I was working on some record and replay prior to my internship at F5 too. But at that point, I wasn't considering interfaces modeled with the component model. I was just considering arbitrary interfaces to WebAssembly as import functions. So there, you don't actually have as much guarantees on how the function interacts with the Wasm boundary. So you need to be much more conservative of about how you record things. Like you have to record your entire memory segment, or you need to have some prior knowledge of how each of these imports operate, which actually makes recording pretty infeasible in production. In that case, you get overheads of up to like 200%. There are some papers out there like Wasm R3 that do this with bytecode instrumentation. But sort of the key thing I realized during the internship is that with the component model specification and the fact that you're implementing it within an engine, which means it's not a bytecode instrumentation layer, it's something built into the engine that's running, you can actually get surprisingly low overheads. So initial experiments with some of the work I did at F5 have shown overheads of below 10%.
Woo!
for full recording, excluding I/O. So kind of the interesting use case here is if you have like short-lived Wasm processes, you could just record things in an in-memory buffer, which means you're not losing any overhead from I/O. And the moment you have a crash, you just log those traces to disk or some persistent storage. And so that is actually very surprising. Like that surprised me a lot. I was imagining overheads of like 25% minimum. And 10%, by the way, is like, I haven't hyper optimized this. This is sort of like,
First
in
try.
my terms, like a debug kind of implementation. So we could really hyper optimize this to make it much faster. And that has been really exciting and I think really promising for next steps towards time travel.
Got it.
Yeah, it's really exciting.
Now, for time travel debugging, what does time travel debugging give the average developer that they don't get with a traditional debugger? Can you kind of elaborate on that?
Yeah. So when you think of traditional debuggers, I would go with something like GDB that people use today. You have like a GDB process you can hook up to your executing Wasm module, and then you can do sort of these user-friendly things like set a breakpoint at memory location, or set a breakpoint at this instruction, or tell me when some variable is written to, or single step to a process in the forward direction, like tell me what signals I've encountered, et cetera, et cetera. Sort of what I see for Wasm is something similar to that in terms of you can take like the engine Wasm time, which I built this into, you can attach this sort of debugging process in step 2 in the forward direction. But the interesting thing with time travel is now you could say stuff like step back in reverse direction, or tell me what was the last time this memory address was written to. And things like that are really useful. So if you think about things like null pointer dereferencing, you might want to know when the last time a null pointer was written to this address. And if you can just set sort of that reverse time step execution, that makes it super efficient for people to debug your code.
Yeah.
In fact, I think even today, most of the bugs in codes come from null pointer dereferencing,
Right.
which is funny given that we have memory safe languages. But that's a rant for another time, I think.
It strikes me it might also be much more effective if you're able to go in the reverse direction at finding things like race conditions, poor interactions between different touch points within the same code. That's really exciting work.
Yeah, I think one thing that I'll add here, when we first started talking to you about doing some of this work, I was enthusiastic about the idea of record replay, but I was a little concerned. Hey, well, actually, if you're just recording inputs and outputs of Wasm functions, that's useful, but in a debugging context, it's not always clear what just I32s and F64s mean, right? But when you started doing the work with it attached to the component model, now all of a sudden we have so much semantic meaning to all these inputs and outputs where that's actually a really big deal. And I'm actually really excited for the future where, we can have something like a really slick UI on top of this thing because we know exactly what these types are. And so we can have a nice canonical representation of what these things look like from any language. And I think we're actually going to have a really stellar component to component or component to host debugging environment, and I really look forward to that day. And it's being pioneered by people like you too, doing all this awesome work.
Absolutely.
So, we're really happy to see you guys doing that work.
Absolutely. Now we are ticking down to time. I do have one final question. I want to give each one of you a shot at this question, and that question is very simple. You are PhD candidates. At some point, that's going to translate into PhD. What comes after that for you? Khan?
So I've been in academia for a while. Like I started school when I was 6, now I am 25. I think when I get my degree, I'll go and work for an awesome company like F5 maybe. So, and yes, I'll probably go to industry. So, and I also, it was my first experience and I learned that the great job is also done in industry and not just in academy. So I learned experience from here. Maybe after that, I may be thinking of coming back to academy and to teach the future students how awesome WebAssembly is.
That's great.
Yeah, it's awesome.
Arjun?
I like building virtual machines, so hopefully I just keep building virtual machines. But
I don't care where I am as long as I'm building a VM.
Yes, that's a Ben Titzer student.
Indeed, yeah. So, but I'm leaning pretty heavily towards industry at this point, at least right after graduation. Like Khan said, I feel like I've been in academia for long. I want to go out to industry, and I think the team at F5 has been fantastic that way. It was a nice small team to work with. I got to work with maintainers of Wasm time. That was amazing, and hopefully I'll continue working with them. And I think at some point I might come back to academia when I'm interested in coming back for teaching, because that's sort of like a direction I'm interested in.
That sounds great.
Yeah,
excellent.
awesome.
Well, with that, that's all the time we have for today, unfortunately. So that is a wrap on fuzzing and time travel debugging, or as I like to call it, throwing Schrodinger's bug at Heisenberg's debugger. Big thank you for Khan and Arjun. It's great that WebAssembly has you working on such interesting research. And as always, thank you to Oscar for his wonderful and sterling co-host duties. Before I go, a quick reminder, determinism is sometimes just a fancy way of saying I can crash the same way every single time. It's a big application world out there. It's time to unleash the power and promise of WebAssembly. And so from all of us, thanks for listening in, and be sure to subscribe for future WebAssembly news and views. Till next time, take care, and thank you.